A lot of this stuff is going to be Xcode 3 for right now. I'm sorry, Xcode 4 for right now. And then it's pretty similar in functionality to Xcode 3. There are a few differences though. So if you guys work on the lab today and you guys are using Xcode 3 to do it, you may find that there's a couple extra hoops that you have to jump through, but the idea is still the same. So in what we've got open here is this is a project called Time Me. It's one of the things that's in the lab for you to just check out. Essentially, all it is just a main that has two function calls in it, Time Me 1 and Time Me 2. Time Me 1 allocates, what is that, 1 million pointers, each of the size I, and Time Me 2 allocates, goes up to 2 million pointers and allocates it. That's all this program does right now. So what I can do is I can under Xcode 4 you've got a profile option. It's similar under Xcode 3. It's the user interface is just a little bit different. So if you guys are using that today and you're trying it out tonight, I'll show you how to use that. So what I do is I say that I want to profile it, and then it switches to this application instruments. This is the primary application that you can use not only for debugging, like looking for zombie objects and looking for leaks, memory leaks, but you also use this for timing to profile your code. So there's a number of different options, CPU profiling options. They all have their own unique way or collection of ways to sample the CPU and sample your program to determine how much time it's taking. For right now, what we're going to just use is the time profiler that basically just counts the number of function calls or counts where you are at in your stack at a specific rhythm of interrupt. So as we run this thing here, you'll see that it fills up here. The time profiler up at the top is actually showing you the CPU usage. The time and the down below here is the call tree, which are the individual functions and the overhead on the individual functions. So every single one of these you can see up. You can see all except the Time Me 2. You can see they're all kernel functions, which is really helpful. It's really handy, right? Because you can see how long each one of the kernel functions is taking, along with you'll see some libraries in here too. If you want to just see your code, just see how much time your code is taking, you can hide the system libraries so that all you see are your libraries or your functions, your function calls. So you can see here that Time Me 2 took 87% of the runtime. Time Me 1 took 12%, and main, the actual main function, only took 0.1%. That's because it just made 2 function calls, and that was it. What's really, really cool about instruments is that you can double click on one of these things, and it'll show you exactly where the most time was taken. What's really interesting, there's a couple really interesting things that we notice here. One is we did twice as many memory allocations in Time Me 2, but Time Me 2 took what is that, almost 8 times as much time to complete than Time Me 1. And so this is a great way to figure out why. Another really interesting thing here is that memory allocations was 5% of the time, but freeing it up was 95% of the overall was the total time, which is pretty surprising to most people. It was actually really surprising the first time I saw it too. So this is showing you down at the function level, broken down at the function level by how much time each one of these functions took themselves. You can also look at this as a top-down tree-like structure where it says, okay, the start is the header code that's put in front of every executable. So it's saying that, okay, 100% of the time was spent in main. And so you can see here, if we want to look from the top down, we can see that time me1 took 12% of the time and time me2 took 87% of the time. You can drill down as far as you want to here, and you can see that's the actual running time on the left, and then that's the percentage of the running time of the whole on the right here. Another really handy thing is that if you look over here, if you open up the view on the right-hand side, you can see extended annotations for each one of these, for each one of the lines that are being showed in the profiler. You can. I'll show you some other annotations too. So that's one example of using the profiler. Let's try another where we do two different versions of the factorial. We'll do an iterative version of factorial here, where it's just very simple for loop, and then we'll do a recursive version of factorial, which is here. Right, two very simple functions, but two entirely different algorithms for entirely different algorithms on the surface to calculate these, right? So what we'll do is I'm going to instrument it, profile it. It's running. We can see right now that as it's running, it's taking 100% of the CPU time, and 98% of it is being spent in the iterative factorial for right now. That's because it's calculating. What do I have? It's calculating what is that? 10 million? 100 million. Wait. 2, 3, 100 million. Yeah. Those numbers may have been left over from. They were probably left over from a stress test that I was doing on this. Or actually, it may be finished, actually. It is finished, actually. Sorry. I didn't see the recursive version because it's down off of it was down past the system library. So 99% of the time spent in factorial iterative, whereas 1% of the time was spent in factorial recursive. And we can, if we look at the you can actually take a look at the output from the console. Under the view here, we can see where is that? Is it the run browser? No. Oh, come on. We should be able to see the. Oh, where is it? I should have looked this up ahead of time. There's a way to see the output that goes to standard out while the thing is, or after, while it's running or after it's run. And God, I can't remember where it is. I'll hunt it down and post it up on the site. But which is really interesting, right? I mean, if we take a look at it, so it's saying that a third of the overhead was just in the function call itself, and then 66% of the time was spent making the actual recursive call. And whereas in the iterative version, 80% of the time was spent doing the multiply. 20% of the time was being spent iterating through the loop. Of course, if you look at this and you look at recursive and you try and break it down, right, you'll see just you'll see level after level after level of the recursion. There's an option over here called flatten recursion that puts it all together. That slaps the whole recursive call together into one lump time. Which is interesting, right? Because you wouldn't really expect the recursive call to be 1% of the time and 99% of the time being taken in the iterative version. So what I'll show you now is that it's much easier to profile these projects if you're running the debugging configuration, because it has a lot more symbols in it, and it's also not doing really heavy optimization. I mean, you definitely want to instrument your performance on your release version, but while you're debugging, it's not a bad idea to run it as well, just so you can see, you get a lot more detailed information. And the other nice thing is that it's not super heavily trying to optimize either. So if we build this for release, the release version, and then we profile it, see that it's done already, and it's all done in the main, and it's split 50-50, which is more of what we kind of expect. But what's interesting is that it's actually these function calls here, or these two functions, quote unquote, the iterative and the recursive, are actually in main itself. The optimizer is actually hoisted the functions and put them directly into main, because it knew that it was tail recursive and it could do it completely in line. So it's convenient to look at the optimized version, but it's like debugging the optimized version too, right? I mean, it's imperative that you look at the release version, but it's also like trying to debug the release version too. The optimizer can do so many squirrely things with your code that it can sometimes be difficult to really figure out where you might be having bottlenecks. So those are trivial toy examples. There's a couple more in here where we do Fibonacci and do Fibonacci memoized. You can take a look at that, and then that's an OS 10 app that I've done. Something that I put together not only for performance and optimization, but also for debugging, is this iOS app called Slow and Buggy. That basically what it does is just presents you with a text field with numbers. You put a value of numbers that you want to have sorted in here, and then a whole different array of types of sorts. Like we can bubble sort it and see the time that it took and what the throughput was. Selection sort, insertion sort, quick sort. There's a hog memory sort that basically sorts, but as it does, it allocates memory so that you can check for leaks. There's also this spawner button down here that actually will spawn a thread that will do BOGO sort in the background. If you guys familiar with BOGO sort, you heard of that? So here's BOGO sort. Check to see if we're sorted, and if we're not, randomly swap values, then check to see if we're sorted. Randomly swap values and check to see if we're sorted. Not the most optimal. Anything over, actually, I think it's anything over about 30 or 40, and it pretty much just runs forever. Here's the rub. So you can do instrumentation directly from here through the simulator. For some reason, this latest version of Xcode, I can't get the simulator and the instrumentation to talk to each other correctly. So whenever I try and profile this app, right now, CPU, iOS simulator, and I profile it, the app starts up, it gets all ready, and no data seems to be getting collected in here. What's worse is that I can't stop it, and actually this has become totally unresponsive. So here's what you can do, and you can do this with any of your applications, or you can actually even do this with applications that you haven't even written. While the thing is running, you can start instruments up, and this is actually the easiest way to do it under Xcode 3 too. You start instruments up, you select which type of instrumentation you want to do. And we're going to do another time profiler. Then here in your target, you look for your process that's currently running. So what we'll do is we're going to attach it to a process. Here's all the applications that are running right now. Here's the applications that are running under the system. And here's Slow and Buggy, the iOS app that's running on a simulator. So what we'll do is we'll connect to that. We'll select that and connect to it. And then we just hit record. And it'll start recording the application and comparing the symbols to the symbol file that is generated with it. So we can say run bubble sort, and you can see that it started to collect information here. Our time was spent in, sorry, let me go back here. Our time was spent in sort. It was spent when we pressed, 100% of the time was spent when we pressed the sort button. Let's see, so when we got an event, when we got a controller, we got a touch event in the window. So you can see you can pretty quickly get overwhelmed with information. So you can hiding the system libraries helps a lot. Hiding missing symbols if you're instrumenting an application that doesn't have a symbol file with it, you'll tend to get just a lot of memory addresses, which isn't very helpful either. You can also specify that you only want to see Objective-C calls or Objective-C trees. So what we'll do is we'll take a look here, and that is the time that was the most time that was spent when we pressed the sort button. But most of our time was, or all of our time was spent in UI application main, which is actually still running right now. So let's flip this call tree over and drill down here, and we'll see that the sort. This is where the time, all the time was being taken. That's the breakdown of 100% of bubble sort time, and you can see that a third of the time was spent comparing the integers, and an eighth of the time was spent swapping the integers, and 50% of the time was spent putting a temporary variable in one of the array slots, which is actually kind of surprising. I wouldn't really expect this kind of coverage. I would expect this to be much more even. Pulling the temporary out of the array, getting the values out of the array and putting them into the new position in the array, and then moving the temporary into the array. I would figure that this would be a lot more even, and it's not. So there's another application that you can check out. We can take a look at we'll take a look at the memory profiler, and we will attach it to Slow and Buggy, and we will start recording, and then we're going to switch over here, and we're going to say we want 10,000 memory allocations. Wow, that was fast. Okay, let's do 100,000 memory allocations, and as that's running, you can see that the allocations, you can see the call stack of where these allocations were being made. You can see the size of the allocations, which is pretty cool. We can take here and find out that it's over 3 gigabytes already here, and we pretty much hit the machine max, and I think it quit. Yeah, so it quit out. So that's one way you can tell when or why your application may have crashed or may have quit. Yeah, so we ran all of it. We had 3 gigs of memory allocations, and then the application bailed on us. So that's a little less trivial of an example of things that you can instrument, and it's really interesting to watch, especially if you do it in comparison to if you're looking at algorithms in comparison with each other. So we'll do the iOS simulator. We're going to do the CPU. We'll do time profiler. We're going to connect to our process, Slow and Buggy. We're going to start recording. We'll switch back to the simulator, and we're going to say, okay, I want to sort 10 or 100,000 random numbers. Let's do a selection sort on it. Let's compare it to, once that finishes. 12 seconds. Then we can compare that to an insertion sort. And you can see, like right there, you can see the percentages of time of each one of these algorithms compared to each other, which is really handy. Do a quick sort. Does that even show? I don't even think that shows up. Yeah, there it is. 12 milliseconds to do a quick sort. 100,000. We could also take and spawn in the background, spawn on a background thread a BOGO sort of 100 numbers, and you can see that's running right now. You'll see that you can split threads off so that you can see them independently of each other, which is really handy if you're doing multi-threaded performance evaluation. Let's hide the system library so we just see our results in the call tree. We can take a look at the number of samples. We can see all of the timestamps for all of the samples that have been taken so far, which is pretty cool too. You can see which CPU it allocated to, or which hyperthread it allocated it to, which is actually pretty amazing. Oh, there's the console. Knew it was in there somewhere. So that's still, I believe that's still running. Yeah, still trying to BOGO sort 100 numbers, which I don't remember if 100 ever finishes. You can always stop it. If you stop you can always stop recording at any time. The cool thing too is that you can record different sessions and you can compare them to each other. So we can take a look at run 1 versus run 2. So you can store up a whole bunch of different sessions, instrumentation sessions, and then you can compare them to each other, which is really powerful. So we can say, okay, let's compare the call trees with both the versions, and we can see which one was more efficient to the other. So a common thing to do is to write your program, debug it, and then profile it, and then optimize it, and then profile it again, and then compare it. And you can compare it. What's really powerful is you can compare it call by call by call, which is way more powerful than sitting there with a stopwatch and trying to time the beginning and end of execution, whether it's a virtual stopwatch or not. So let's take a look at something that is more that is a bit more less academic. So this is Bouncy, the Bouncy program that you guys may or may not have finished. So what we're going to do is we're going to build it, and we're going to start running it. And we're going to do the same kind of process here. Oops. Do that. Kevin's going to have to do some editing now. Kevin's not going to have to do some editing of the quick time capture. Time profile. Use Bouncy iOS. Start recording it. So here is, not surprisingly, but well broken down, which is really helpful. You can see that core graphics is taking 20% of the overall time. You can see that it's in, or 20% of the time is in AA render. 10% of the time is in color mask copy with alpha RGB 8888. So that's the quadruple 8, the 8-bit representation of alpha red, green, and blue color mask fill. So we can see all of the core graphics calls are the majority of the time. If we hid the system libraries, we can see that Not surprisingly, that iOS View's draw rect is what is monopolizing the CPU time, right? And then we can go through and we can see that it's being called from main. If we double click on it, we can see that fill is taking a third of the time, which is actually pretty interesting. A third of the time is in the fill, and almost 2/3 of the time is just in drawing the outline around the shape, which is, I wouldn't have quite have expected that either. We can take a look at only Objective-C calls, so we can get rid of the other C calls that are in here, like crect make. We can stop instrumenting it, and we can take a look. We can go from the top down, and we can see that, obviously the draw rect timer fire method is taking up 2% of the time, and you can see that 57% of the time is being handling the collisions between the objects, and a third of the time is being used in just setting that our view needs to be redisplayed, which doesn't actually do. I don't believe it actually does the drawing right there. I think it does come back out from the event loop and come back, or the run loop, and come back in and actually make the draw rect call. That may be short-circuited under the hood, but you can always find that out by not hiding the system libraries and then drilling down in here and seeing that, okay, let's see, here's our timer fire method, and we can take a look at the raw assembly and see exactly what the breakdown is, and we can see if it actually does. It actually looks like it does make a direct call at that point as soon as you call set needs display, which is also interesting. Questions? So you guys basically the lab today is you can download these projects or not. You can start with something very simple like a OS 10, like a command line program is actually pretty much the easiest one to instrument, because you don't have to worry about the Objective-C aspects of it. If you're feeling a little more comfortable with it, do an OS 10 Cocoa application, and then the next step after that is do an iOS application, which adds a layer of indirection, so it's not quite as straightforward to instrument. It's especially a little more difficult with Xcode 3. One cool thing about Xcode 4 as well is that Xcode 4's instrumentation is that you can actually set up automated tests you can set up touches and taps and drags and pulls from inside the instrumentation to run unit tests or to profile your profile for optimization. And you'd be surprised that how many people kind of there's one of two main camps here. One is optimize way too early, like they're constantly thinking about optimization and profiling their code before they've actually even finished and debugged it and even thought about like maybe replacing the whole algorithm. So they tend to spend way too much time, burn up way too many cycles, save the profiling and the optimization at the end, unless there's something really, really bad. Unless you're finding something really bad that may change a lot of your code, like maybe your memory management. Save the profiling to the end. Or there's also the camp, especially the iOS device camp, that says, well, it's just going to run as fast as it possibly can on the device, and I can't do a whole lot about it, so I'm not going to spend a ton of time optimizing or profiling, which is a really, really big mistake. If you take a look at the research numbers that talk about user responsiveness and usability of an application and retention of an application on an iPhone compared directly to responsiveness of that application, it's almost a one-to-one correspondence. The less correspondent, the less responsive your application is, the faster it gets taken off of the phone. And the more likely it is no one will buy your products in the future because they realize that you haven't gone the extra mile to profile and optimize. So it's definitely worth spending some time getting comfortable with and using this thing. And that's pretty much what today's lab is. And it gives some suggestions, not only some of the things that you saw in here with like trying iterative versus recursive, but also doing things like you saw the memory management stuff, but maybe checking the containers, the performance on containers, whether they're STL containers and iterators, or you're checking NS object or NS arrays, NS sets, seeing which one might actually be faster under the hood. And then there's also checking threaded stuff too. There's also checking like using OpenMP and taking a look at how well it can distribute your threads, using P threads or even using NS threads. That's all supported by the profiler. Cool. Questions? Probably a lot, but hopefully if you experiment with it, it'll give you a good feel for and play around with it. The lab has also got the documentation. This is the primary documentation here, the user's guide. Then there's some specific documentation for tuning iOS apps, and then there's online. There are Xcode 3 like step-by-step tutorials to go through and using instruments on Xcode 3. Yeah.
Did you show where the actual instruments tool is?
The application is? Sure. That's.
What would it be in Xcode 3?
Yeah, so it should be under. I'm pretty sure it's in the same place. It's under in developer applications instruments. I'm pretty sure it's in the same place as actually I can check that right now. Yes, same place. Yep. Cool. Yes, and it really has to do with so here's my guess, because they're the same when you turn the optimizer on, right? So what I'm guessing is that because in the past recursion was so prohibitively expensive space and time wise, that compilers, even if you're doing a non-optimized build, compilers will still look for tail recursion. And when there is tail recursion, it'll turn it into a loop. Like it'll optimize that just by default, because it's such an expensive operation to have that tail recursion. That's actually you can actually check that out if you put some code in there to do some work and force it not to be able to tail optimize the thing, and see if that balances back out, or even gets even worse, or gets very unbalanced on the recursive side, because now it has to actually save up all those stack pointers. That's my guess. I'm not entirely sure. So that's actually a good thing to maybe try out. Even try that out tonight and see if you can force it to choke on the recursive. That really surprised me too the first time I saw it. I was like, yeah, I must have left a 0 out or something. So you're asking about the if it runs slow in the debugging version, but doesn't run slowly in the release version. Yeah, if you're going to be releasing the release version, that's your final metric, right? So that's the one that I would trust as your final and use as your final number. So if you know. Because a lot of times if you put a lot of debugging code and a lot of testing and a lot of like assertion checking in there, you'll see that a disproportionate amount of time is being spent in debugging code as opposed to like your actual production code. When you do a release version that strips all of that out, now you'll see like where the real time is being spent and where the bottlenecks are. That's what I would. Since that's going to be what you're ultimately going to be releasing, that's where I would spend my time, like fixing the code up. I'm just letting you know that it's a lot more difficult to determine exactly where bottlenecks are when you have all of that, the heavy optimization turned on. But by the same token, one of the beauties of instrumentation is that is by saving runs across runs, you can try out and experiment with optimizations and then compare them and compare and contrast and see how that not only affects like that function you're working on, but how that affects the system overall. Because you see like all in one glance at like what's actually been sped up and what's actually slowing down, which is actually pretty cool. So yeah, that should be your final word of truth is the release version. Just know that it's a little bit tougher to track down optimizations in the release version. Cool. All right.